Hi, I'm George Kondiles, Chief Architect and a co-founder here at Ocient. Today, I'll be talking a little bit about our loading and transformation infrastructure. Now, Ocient, as a hyperscale data warehouse, focuses on the analysis and querying of extremely large data sets. But in order to analyze extremely large data sets, one must first load extremely large data sets. To that end, Ocient's loading and transformation technology and its infrastructure is a key and integral part of what we do. We talk about the firehose, a veritable deluge of information flowing in from a variety of possible sources. Things like S3, where we might have some large number of CSV files sitting and being passed through, or a queuing system like Kafka, which may have something like JSON documents. Regardless of the exact source, the network boundary at which the rows are arriving to us receives an extremely high volume and large amount of information. And dealing with that, loading it and storing it in our foundation layer is an extremely challenging technical problem. What I'll be discussing here are a few of the design principles and goals that we considered when tackling it. The first is linear scalability. Second is low time to queryability. And the third is exactly once semantics. Let's dive in. For us, linear scalability refers to the fact that our system, as measured in a total number of rows per second or bits per second, from the network boundary to eventual storage on our foundation layer, is a linear function. Its capacity in that regard is a linear function of the number of loading nodes present in the system. Therefore, the loading unit, or the scaling unit of our system is the loading node, where each one operates on a disjoint subset of the inbound firehose. And when we deploy systems, we essentially determine the total throughput rate based on requirements and multiply by the loading capabilities of one node to achieve the required results. Now, from a linear scalability standpoint, a system might be theoretically linearly scalable, but if the number of individual nodes required to meet a certain desired throughput was impractically large, we wouldn't call this system as a whole as practical. As an example, if I required 1 million loader nodes to load one foundation node, we wouldn't call that a system that anyone would want to install. To that end, our job has been not only to be linearly scalable in the number of individual units, but also to make each individual loading node as high throughput as we possibly can. We achieve this by following similar design principles to that we follow in the database engine itself. Fundamentally, this follows a pattern that we called resource-aligned parallelism, where the number of disjoint processing units is aligned with the actual physical system's processing and I/O capabilities. Then, within each loading node, the amount of information that it is processing is further subdivided such that each of the disjoint processing units within the node is working on a subset with minimal coordination with the other units in the same node. Now, it's difficult to say exactly how much throughput or rows an individual node can handle. And this is because the exact number varies fairly significantly based on schema complexity, the number of indexes, and so on and so forth. However, by following this overall disjoint, shared nothing, resource-aligned approach internally, we generally see that loading nodes on average can handle at a minimum of multiple gigabits per second of total data rates or multiple millions of records per second in row rates. And it's via this approach that we aim and are generally able to minimize the number of loading nodes in this linearly scalable fashion required to meet a given installation's requirements. The second major point is low time to query ability. And what this refers to is the fact that while Ocient's system is one for processing large amounts of information that can span either months or years, it's often the case that the most recently loaded information is of particular importance and sees a larger fraction of the analysis. This also means that enterprises generally would like access to that information more quickly. And when we say low time to queryability, what we're referring to is that when a particular record, let's call it record IX, is presented to us through the firehose from one of the variety of possible sources, that it eventually is made available for querying. And I'll draw a basic query plan with some I/O operators over here to eventually return records back to the end user. When we talk about this record IX, it should, if a query should return it, be made available on the order of seconds as opposed to minutes or hours or days. In order to achieve this, we must talk a little bit about how Ocient stores information in our foundation tier. We have on our storage and compute nodes what we call a long-term store. And this long-term store is where we place our fundamental storage unit that we call a segment. Now, as a data warehouse, Ocient follows the general pattern of write once, read many. We overall expect an individual record to be read many times off of disk. So it's often worth the upfront computational effort to make these segment storage structures as compact and efficient as possible. However, in order to produce the compact and efficient segment structures, we often need to apply computational effort that would be prohibitive to making a record available for querying quickly. It's kind of the exact opposite of what we want. We want to spend as much time as possible getting enough information in place so we can make nice, efficient storage structures on disk. But when we're doing that, we're also not making the record available for querying. To account for this, Ocient employs a second storage layer in its storage and compute nodes at the foundation tier that we call our immediate store. And this immediate store stores a much smaller unit of data that we call a page. Now, pages are pretty much the exact opposite of segments. They're designed to be smaller, and we apply minimal computational effort up front in generating them. In fact, it is one of the primary goals of the loading node to take a given record and eventually store it in a page as quickly as it possibly can, i.e. seconds. And that is particularly getting it into that storage structure that quickly that enables the low time to queryability. Now, from an I/O perspective, when queries are actually executing, it's entirely transparent to the end user which of these two stores we are consuming at a given point in time. The I/O layer will access both the long-term store and the immediate store in parallel during query execution, enabling records that have been sitting around for years, as well as records that have been sitting around for seconds, to be addressed by the same query with no extra effort on the user's behalf. Now, the loading nodes have one additional job. We eventually want to end up with our write once, read many, highly efficient storage structures on disk, but the data is stored in these high throughput pages instead. So loading nodes not only generate the pages, but they also, in the background, go through a process that we call a page segment swap, where they load groups of pages, generate segments from them, and then place them back into the storage layer. Now, this all happens in the background without any user interaction, and on the whole, gives us the best of both worlds, where records are made available for querying quickly, but eventually are made available for querying efficiently at a short time in the future. The final topic is exactly once semantics. Now, any distributed system needs to be capable of handling faults, errors, and issues that arise when you're working with large numbers of disparate systems and networks and so on and so forth. And as a key tenet of being a database, it's important that anytime a user executes a query, that we always return the same correct result. In the context of loading, what this means is that if our given record, IX, is loaded into our system and stored either in a page or in a segment, and should be queried, i.e. the query could theoretically address it should the predicates and the filters match, we need to make sure that we return that record exactly one time, not more than once and not 0 times. We can't lose the record. Now, systems generally provide this in a variety of different ways, and to some extent it requires a bit of a coordinated dance with the source system providing the records and the system doing the loading itself, i.e. the Ocient storage and loading and transformation infrastructure. However, in our case, we do most of the heavy lifting for the entire system. And the way this is primarily achieved is via the usage of idempotent puts. When the record IX is inserted and stored, the system as a whole guarantees that if the source system were ever to send IX again, that we will not send it out, the queries, more than once. It may be stored in multiple places, but we will deduplicate it at query time, enabling the correct exactly once semantics to take place. What this means is that the source system need only guarantee that it understands what it believes is stored, and then in the case of any fault, whether it be the loss of a node or a network connection or a disk or whatever else, if it's unsure of the current status of a record, it should resend it. Now, we wouldn't want to be deduplicating everything forever, because the kind of implication here would be that the source should just always send everything over and over again. And obviously, the amount of overhead with that would be unreasonable. So there is a second component to this. And essentially, it's the backwards signaling to the source system indicating which records have been made durable. Some systems use a mapping scheme internally, some sort of associative structure stored on the loading nodes to understand what has been made durable, as well as to do the deduplication as we've been discussing. However, there are some problems with a mapping-based approach. The biggest one is that that map is often located and stored on the node doing the loading. And so in the case of faults on a given loading node, we potentially risk losing the deduplication information as well, possibly making it the case that if an idempotent put were to happen to replay to a different loading node, that we could actually end up with 2 copies of the record in the system because we lost our map. Ocient's taken a slightly different approach, and it's one where we define the flow of records as 2 ordered streams, one going in and one going out, where each record has a position in the stream, and going back out are are acknowledgments of durability of a record. So the source system need only subscribe to this contract. Send every record at or after the last record that the system told you about being made durable. We call this the durability horizon. The horizon being the most recent record that we are guaranteeing has been stored in a reliable and durable way on the requisite number of nodes in our layer, the foundation nodes, to make available for querying, and the source system need not send them again. Now, this simple durability horizon-based approach based on ordering has one key and important feature, and it is that it is computationally cheap to calculate. And we can store that information in the consensus protocol that we enact on our foundation clusters. Fundamentally, what this means is that the loss of an individual node within the loading infrastructure does not mean the loss of the durability horizon information in the foundation cluster structures. So that when another node comes up and information, potentially duplicate records, are forwarded through a different loading node, we're still able to deduplicate it. This has been a bit of an overview of some of our key design philosophies and some of the things that we built to produce a high throughput, reliable, and truly world-class loading and transformation technology. If you'd like more information or have any questions, please visit our website.